Hello, and welcome to this edition of the Satellite Image Deep Learning video podcast series. Today, I'm speaking with Adeel Hassan. Adeel is a machine learning engineer on the Geospatial Technology and Research team at Azavea and one of the maintainers of Raster Vision. He joined Azavea in 2020 after completing his MS in Computer Science at the University of Massachusetts Amherst as a Fulbright scholar. His work focuses on the intersection of deep learning and remote sensing. I'll give you Adeel.
Hi, Adeel. How are you doing?
Hey, I'm great. How are you?
Yeah, good, thanks. Looking forward to hearing about Raster Vision. Do you mind telling us what it is and what problem it solves?
Right. So Raster Vision is an open source library and framework for doing deep learning on geospatial data. And the reason you need such a thing is that geospatial data tends to differ quite a bit from your ordinary images. For one thing, you can have multiple bands if you're using multispectral imagery or hyperspectral or what have you. Then there's also the fact that the geospatial imagery tends to come in the form of very large rasters. So you need some way to chip it down to smaller, more manageable sized images. And most importantly of all, geospatial data tends to be georeferenced. So that is an important thing to keep in mind when you're, for example, trying to align your imagery with your labels or combine different sources of data together, is to make sure that they're geographically aligned. And similarly, in terms of your model output, you also want to make sure that is georeferenced because that is the way it will be most useful for further downstream analysis or whatever application you're using it for.
Fantastic. So it's basically handling all those very geospatial specific pre and post processing tasks, whereas
that's right.
And actually even assisting with the deep learning training itself.
Exactly. Yeah.
Fantastic. It would be great to have a look at the documentation and start to get a feel for it.
Sure. I'm going to try to share my screen now. Awesome. Right. So this is our GitHub repo. Just a bit of note on the installation, you can install it via pip, or you can use one of our Docker images or build one yourself. But what I'm going to do is jump straight to the documentation. And this is our documentation site. We recently redesigned it a bit to be more useful. Now, what I'm going to do is start with this usage overview page. And as I've said already, Raster Vision is both a library and a framework. So let's take a closer look at what that means. So a library, as you know, is something you can just import stuff from and then use it in your own code and go build other things with it and so on. While now this part is actually new in our latest release of Raster Vision. Historically, it has been more of a framework, and what that means is that you would create an entire Python file with this get config function that was supposed to return a specific kind of configuration. So, for example, here it's showing a semantic segmentation config, and so what that does is it describes the entire semantic segmentation pipeline from the reading of the data to predictions and evaluation. And as you can see, it doesn't really require the user to write their own code for the most part. So this is kind of ideal for non-developers, of which we have a lot. Like they make a significant portion of our users. So people coming from the GIS world. And so they usually find it easier to configure it this way.
Interesting. And that was supported with some command line interface, or would people actually use this script to generate a config file that could also be manually edited, I suppose?
Correct, yeah. So you would define a file like this, and then you would call Raster Vision from the command line, as shown here. So I'm going to come back to the Raster Vision pipeline in a bit. What I want to start with is this library expect. And what you see here is an example of a geodata set, of what we call a geodata set. And this is kind of an important concept in Raster Vision. What it does is basically provides a bridge between the geospatial data world and PyTorch world. So as you know, PyTorch has this concept of a data set which you can then turn into a data loader and read data from. And it doesn't really matter what the data set does internally, as long as it provides an interface that the rest of PyTorch can use. Right. So geodata set provides that interface for geospatial data.
Right. And because I think data sets in PyTorch, they need to be like JPEGs or PNGs, for example. You can't have data sets of GeoTIFFs, I assume.
That's right. Yeah. Basically, the function of a geodata, a data set in general, is to provide is to output data in the form of PyTorch tensors that can be directly fed into the model, and the way it converts raw data into those tensors is left up to the data set.
Right.
So this example is showing an instance of a semantic segmentation sliding window geodata set, which, as you can tell from the name, is a geodata set that breaks down a large geotiff into smaller chips in a sliding window fashion. So you start from the top left and then you slide the window along. And it's specifically for semantic segmentation. That means its outputs are an image and the labels in the form of a label raster, because for semantic segmentation you need pixel-wise labels.
Right. And so by having this approach with a library, you basically make it much more flexible. You can use just this data set and all your other PyTorch code. Whereas if you have the framework, it's a bit more bundled together. Right. Okay.
Right. So if someone is coming from a machine learning background but are not familiar with geospatial data, they can just use a snippet like this, and right away they have a data set that they can plug into their usual machine learning code. So again, in terms of the library functionality, we have a bunch of tutorials here that consist of Jupyter notebooks that go into a lot of detail about how to use specific features of Raster Vision. And what I actually want to do now is to start with this PyTorch Lightning notebook or tutorial, and just to give an idea of what an end-to-end workflow might look like. And in fact, let me switch over to my Jupyter lab, which I have running locally.
And just briefly to say, for people that are not familiar with PyTorch Lightning, it's basically a higher level API on top of PyTorch, isn't it?
That's right. So the motivation for this library is that normally when doing machine learning, you need to write a lot of boilerplate code for training, and like you need to define a loss function, optimizers, data loaders, and so on. And so PyTorch Lightning comes built in with that kind of code, and you can simply override small parts of it to customize it for your use case, and then it just basically speeds up the process a great deal, and it's become quite popular these days. So in this notebook, we first make sure we have Lightning installed, which I already do. So let's skip that. Then we're importing a bunch of stuff from Raster Vision that we'll see below. And for this example, we're using an actual public data set that people might be aware of called SpaceNet2, which is from this building detection competition from some years ago. And we're going to use a small toy data set, so a single scene, which consists of a GeoTIFF as our image and a GeoJSON file as our source of labels. And so the label file contains polygons that delineate buildings, and the image raster Also, you might notice that these URIs are S3 URIs. And one of the neat things about Raster Vision is that it can seamlessly work with local URIs, S3 URIs, HTTP URIs. So it doesn't really care what you feed into it. It will, if it doesn't have the data locally, it will fetch it, download it, or upload it.
Nice.
So one of the important things you need to do at the start of most Raster Vision tests is to define your class config, which basically means defining your classes for your machine learning test. You can also specify colors optionally, or you can skip it and have Raster Vision generate them for you. These are mostly useful for visualizations, as we'll see below. And we're also defining a data augmentation transform as you normally want to do when training. And Raster Vision supports the Albumentations data augmentation library, which is one of the most popular ones for this, for this purpose. And this is our data set initialization code. Again, we have a semantic segmentation geodata set, but unlike before, we have a random window geodata set. So as opposed to a sliding window, this samples windows at chips at random from anywhere within the raster during training. And we have this convenience method from URIs that allows you to basically do it in a single call. But if you do want to like dig deeper and do something more customized, you can also do it in a different way that we'll also briefly look at later. And so yeah, we're passing in our class config, our image URI, our table URI, and we're also telling it that the polygons in the GeoJSON correspond to the building class. And we need to do this because the GeoJSON does not specify what the class of the polygons is. So, so you can instead have a GeoJSON file that has a class ID field for every polygon, and in that case, you won't need this.
Right.
And we're specifying size limits. So the random windows that we sample can range anywhere from between 300 to 350. And they will all be resized to 325 before returning. And since this is a toy example, we're only going to sample 10 chips in total. And this is the transform. Now you run it. It will download the file, which should happen fairly quickly because these are small. Yep, we're done. And so just to again emphasize what having a data set means is that you can do stuff like sample X and Y from it, and X is your image of 3 color channels, and Y is your label mask.
Yeah.
And Raster Vision also provides this visualizer class, which allows you to visualize your input data in this standard format. And I'm not going to rerun this cell because it shows something important currently. That you can see in this last one that the colors are a bit weird. And this is, again, one of those idiosyncrasies of geospatial data, is that these images are 16-bit integers, and they have a wide distribution of values. So if you were to open this in QGIS and plot the histogram, you can see they're kind of all over the place. And so what that means is that when we normalize the data before feeding it to the model and also before plotting it, that kind of your outliers in one channel can affect the values of all the channels and make it look slightly weird.
Yeah, so that's something that wouldn't be in regular PyTorch, right? Because in PyTorch, you're usually using 8-bit images, and you don't have this massive range of possible values to deal with.
Correct. Yeah. Now Raster Vision also provides a way to deal with this, to normalize it in a more principled way. But it turns out it's not always necessary for the model to train Like if you don't do anything and leave it as it is, the model will train just fine. So we're going to do this for now. So just as with the training data set, we create a validation data set. In this case, we're using a sliding window because we want to make sure we get the entire raster. And here's the machine learning part. We define a few things. We create an output directory, define epochs, batch size, learning rate, data loaders is all normal. And here's your Lightning module, which this is basically the part that you need to override to customize Lightning for your use case.
Yeah.
And so we're here, we're going to use the deep lab model. And we override the training step. It's pretty basic. We just pass the image through the model, forward it through the model, and then use cross entropy with the mask. Similar for the validation step. And
this is all just regular PyTorch and PyTorch Lightning, isn't it? So this is nothing Raster Vision specific.
Correct, yeah. There's nothing Raster Vision. Yes, so we're only using the dataset part of Raster Vision right now. So yeah, you have your Lightning trainer, and what this shows is that you can also optionally use TensorBoard. This is just a screenshot, but you can. It's possible to run TensorBoard from within a notebook, and you use that to track your experiment. And finally, we can call trainer.fit. And yeah, we're training it for 3 epochs, and it should go by pretty quick.
Nice.
Yeah.
So I can see how this would immediately save all that headache where people typically have to sort of chip up an image and create a bunch of other images and use that as the data set in the right, format with PyTorch or whatever. So it helps you with the pre-processing. It also helps you once you're inferencing images that are geospatial as well. That's
right. Yeah, we're going to look at it shortly.
Cool. And just another question. It supports PyTorch, obviously, but does it also support TensorFlow?
It does not currently support TensorFlow. Actually, on a historical note, it originally only supported TensorFlow because originally the project started back in sometime around 2017 or 2018 when PyTorch was still fairly new, and TensorFlow was the go-to framework for deep learning.
Yeah.
And so the first versions of Raster Vision were based on TensorFlow, but as we saw the popularities flip and PyTorch take over, we decided it made more sense to switch to PyTorch. Okay, so we have our training done, and we can take a look at inside our output directory. We have Lightning logs. Now we're going to do some predictions, but we're going to cheat a bit because it turns out 10 windows are not enough to train a decent model, but we want our predictions to look at least somewhat good. So we're going to load a pre-trained model from S3. And so this is our same model architecture, we're just loading weights. And yeah, so now you have a PyTorch model and you have your prediction data set. In this case, we're going to be predicting over the validation data set. But regardless, even if you wanted to do it on a different image, you would just create a new data set as we did before. And now you can proceed to do predictions however you want. Like over here, we're doing it in normal PyTorch code, but if you want to use some PyTorch Lightning utility for doing that, that's also fine. So what Raster Vision expects is basically an iterator over the prediction outputs. So basically, we're defining a get predictions model here, a function here that iterates over the data loader and yields predictions one by one. That's all to kind of avoid having it all in memory at once. And so once you have an iterator in the form of a generator or even as a list or something, you would then pass it to this labels class, specifically the semantic segmentation labels. And what this allows you to do is do things like, for example, when using sliding windows, you can have a stride that is smaller than the window size. So what that means is that you would be hitting the same pixels multiple times as you do predictions, and you can then average those predictions to do some sort of test time augmentation, basically. And that also helps you with some boundary artifacts that you see when you do sliding window predictions. Usually the predictions around the edges of the window are kind of distinct and kind of poor relative to the ones in the center.
Okay, so what we're going to do here is predict on the original TIFF files, which are obviously bigger than the window itself, right?
Right.
Yeah.
So yeah, we specify the windows and the predictions, and we run this. Oops.
Yeah.
And yeah, we can query the raw scores of the predictions and visualize them as well. So this is our building predictions on the left.
But it's a really interesting point you raised there, because obviously people usually tile up images, and as you say, predictions cannot be so good at the edges, but actually if you looked at the scores on those small tiles, it might be worse than I assume what you're going to get when you methodologically in this way inference the whole image. So it might suggest that if you really want to understand how well your model is going to perform in practice, this is the only correct way to do it.
Yeah, there's actually a bit more to this. If I can briefly switch to our blog post that we did for the new version. We have an example here of this. So in the left image here, you can see there are obvious edges, right? The horizontal and vertical lines. And Raster Vision actually has a couple of ways to deal with this. The second one shows the averaging that I just talked about. And then third one shows that you can also crop the chips. So you can just discard the edges.
Yeah.
And align your windows in such a way that, adjacent edges are discarded and you only get the center predictions. And you can even combine the two if you want to.
Right. And that definitely looks the least artifacts in that one, doesn't it?
Yeah.
Don't see those sharp lines in there at all. So that's a nice bit of engineering you're taking care of there.
Yeah. And again, this is one of those idiosyncrasies of geospatial data.
Yeah.
And finally, we can save our predictions. So over here, we're saving our predictions here. So we have the labels. I want to open here. So these are your discrete predictions that say whether each pixel is a building or not. And then you also have raw scores. And you also have this GeoJSON. So each predicted building as a polygon.
Right. So this could be directly output displayed in QGIS or something on a map, right?
Correct. Yeah. Yep. It also has this pixel hits.npy object. This maintains a count of how many times each pixel has been predicted. So that if you want to do another round of predictions and combine it with the original output, it allows you to get the math right by going from the average to the sum, basically. Right. So anyway, finally, we can also do evaluations. So compare our predictions to the ground truth labels and see how we did. So for that, we use something called an evaluator. And we're getting our ground truth from the validation data set that we created above. And our predictions are the prediction labels that we defined above. And this gets you output of this form where this is the evaluation of the building class. And the most important thing here are these metrics. So you can see we're getting an F1 score of 0.95 and precision, recall, specificity. But just to note, this is the pre-trained model, not the one we trained right now, because that was kind of a toy
That'd
example.
be a miracle.
Yeah. So yeah, this is the same for the background class, and you can also save this as a JSON.
Yeah, fantastic.
So yeah, this is kind of an end-to-end example of what using Raster Vision as a library might look like.
And you end up with quite a concise notebook in the end, don't you? There's so much boilerplate code that used to be there that is just not required anymore.
Yeah.
And yeah, that's really nice. In terms of, without going into too much detail, I guess there's a bunch of other functionality in Raster Vision as well.
Yep. Let me start with this basic concepts page. This kind of diagrammatically describes what's going on underneath. So if you see in the first diagram, we have the geo data set on the right, which we can directly jump to using the from URIs constructor. But what happens underneath is that there's a concept of a raster source and a vector source. So your geodiff files can get read through a raster source, and a vector source reads your GeoJSON files, and then a label source that converts those labels into a form that is suitable for machine learning.
Right.
And a scene is a class that combines the two things, and it also allows you to specify AOIs at this point.
Right.
And then finally, you get a geodata set, which you can use in a number of ways. We saw how to use it with Lightning, but Raster Vision provides its own learner class, which is you can kind of think of as a parallel to the Lightning module. Because again, Raster Vision precedes the creation of the Lightning library. Or you can use your own custom training code as well. So we have tutorials that cover each of these components. So these are your raster sources. We have something called a rasterio source, which is just a wrapper around rasterio. And it allows you to simply read the file and do basic things like NumPy, like indexing to read chips. Again, I mean, it's basically a very light wrapper around rasterio, but it makes it convenient to do stuff like data exploration, for example.
Yeah.
And I mentioned normalization before. So we have a couple of ways to do that. You can use a min-max transformer, or you can use a stats transformer. So remember that histogram I showed before. So this shows how stats transformer can go from the raw histogram on the left to something more reasonable that goes from 0 to 256. Basically, we also convert to 8-bit integers in this process.
Yeah.
And this allows you to get rid of outliers as well.
Yeah. Okay. Fantastic.
Yeah.
Okay.
And you can do subsetting, reordering. This is an example of a hyperspectral image.
Wow. 130 bands.
Per minute.
Right.
Yeah. In total, it has around 200 or so bands. And you can combine different sources of data. So here, you can read, we have RGB, SWIR, and 2 SAR bands, all coming from different files, but for the same area. And you can combine it using something called a multi-raster source. And yeah, and kind of in the same vein, we have vector sources. I think I'll mostly skip over, but it allows you to do things like buffer geometries. So if you have your roads as line strings in Shapley terminology, you can buffer them into thicker polygons for doing semantic segmentation, for example.
Yeah. And all of this code has been battle tested and developed over a couple of years, so you won't have all those concerns with those one-time scripts that you have to discover all the bugs yourself the first time. Fantastic. Okay, so if people want to follow along with the latest vision updates from Raster Vision, where's the best place for them to do that?
Right. So we have a repo here. We have a discussion forum here, which is kind of the official forum for Raster Vision. Previously, we also had a Gitter, but we are only using discussions now. And yeah, it tends to be pretty active. We tend to get a lot of feedback and questions. So you're welcome to basically just start any discussion you want. Any feedback, bug reports, or problems you're running into. You can also create issues, feature requests, or anything. And yeah, we try to be pretty responsive and help people with their use cases.
Fantastic. Well, thanks so much for providing an introduction to Raster Vision. I'm really looking forward to using it myself and looking forward to hearing how everybody else gets along with it and uses it too. Thanks so much, Adeel. I'll catch you another time then.
Yeah, my pleasure. Bye.
Bye then.